All right, let me share with you the outline here. First, my vision about NLP and its role in AI, and Alec was saying about how important text information is. I kind of remember statistics that about 80% of the world knowledge is in text. Now, I'm not sure how true that is, because a lot of information is in pictures and videos and so on, but text certainly contains a lot of information. I'll say something about dialogue system, different types of systems, and then I'll go into the deep NLP and how do we transform text into some knowledge graphs that offer us a standard way to represent knowledge, and then we can reason on that knowledge. And then about question answering. And so here's an important slide, and shows the vision I had for many years. In AI, we have the problem of representing knowledge and reasoning about the knowledge. I think the slides will be offered to the audience. So, all right, if somebody wants to take pictures, no need for that. So the central problem in AI is how to represent knowledge and how to reason about knowledge. And the AI systems that we have today are representing knowledge in like first order logic and axioms, and those axioms are created by humans. They are not automated. It's very hard to go from text to first order logic. Teaching that to students is really a nightmare. And my vision is that NLP and the tools we can create with NLP can facilitate extracting knowledge from text and transforming that into some actionable knowledge, right? And I'll show you how we can go from text to knowledge representation that can facilitate reasoning. Now, the other hand down here, oops, you have machine learning, and machine learning facilitates natural language processing tools. It's basically present in all the modules, from early part of speech tagging all the way to extracting semantics from text. And machine learning, therefore, enables NLP, but also this way it enables building robust AI systems. Ontologies play a very important role. Ontologies basically are knowledge bases that are dedicated for some domains that represent the most important concepts and relations in a domain. And people build ontologies by hand, and that's a very tedious process. And because ontologies are useful, they, for example, help us with abbreviations. They show the connections between concepts. You build these ontologies hierarchically. For example, you refer to a vehicle, then that's a car, and the truck is related to a vehicle, a sports car, it's a vehicle, etc. So we have to develop tools to build these ontologies automatically, and it's possible to do that. So you start with some important concepts, and then you extract more related concepts, and then the snowballs grows. It's like you build larger and larger ontologies. And then we have here the knowledge bases. This is the result of transforming text into some semantic triples. We build the knowledge graphs. So this picture really shows that NLP is central to all these activities. And if you want to build some large, robust AI systems, then NLP will be a good way to do that. Any questions? The audience is small, so if you have any questions, maybe I can answer them. All right. I know this audience is interested in chatbots, and I want to classify these dialogue systems into, this is how they are classified in some NLP textbooks, as task-oriented dialogue systems and chatbots, which are more intended for extended conversation. It's not only ordering something from a restaurant like you do in a task-oriented dialogue system, but you engage the machine into some dialogue, and then the machine responds, and then you ask another clarifying questions, and eventually that conversation takes many turns. So that's how I look at chatbots. And it's a different architecture, and we have to be aware that chatbots are not necessarily a task-oriented system. There is a fuzzy line, and people can argue that there is no need for this taxonomy, but it's being made in the literature. All right. Now, here's an architecture that I came up with that is for dialogue systems. So we have here the input from the user. Let's see. Let me use my laser pointer here. All right, so the speaker has some question, and that speech is converted to text, and these modules convert speech to text and text to speech. And I'm not working in that area, so I'm not going to say much about that. But once we have text here, then that question will be processed by this NLP unit, and we extract information like what's the intent of the question, what is the focus of the question, what's the question all about, and what kind of answers the user is looking for, etc. And there's a dialogue manager that is present in all these dialogue architectures that really manages the dialogue, keeps track of what questions have been asked, what's the history of the dialogue, and it chooses where this dialogue will go, such that the answers will not be repeated. The response is prepared here, and then it's converted to speech. So this is just the dialogue part. Now, more sophisticated systems need to extract answers from some databases or from some repository, from some documents. So that's where question answering comes into play here. We have now the question being sent to the question answering system, and the question answering system has to find the answer to that question by looking for the answer into some documents. So now there is another unit here, NLP, plus some indexing that converts the documents into some knowledge graph. And this knowledge graph is basically a set of semantic triples. And then certainly the ontology can help with the NLP processing as well as with the question answering. The Solar system here, which is trying to extract answers from the documents, is a hybrid way to help the question answering system such that some answers will not be found in knowledge graph. Maybe there is no match between the question graph and the graph that was obtained from the documents, but still there is some answer into these documents. So to build a system that to be more robust, we send the question to the Solar, and then the documents are retrieved, and then we process those passages further to extract the answer. So we have here an architecture that I think is strong enough to sustain many applications that could be fairly sophisticated. Any questions?
Does Solar stand for something?
It's a way to index documents. Yeah. I don't think it stands for anything.
Just a way to index.
Yeah, that's right. It's the name of an indexer. Okay.
Do you want to give me the thing to change?
No. I can do it. Yes, please.
We're going to be able to access that slide.
Yes, the slides, right? Okay. The slides will be made available.
Repeat the question if people ask questions.
Okay. So the question was, what does Solar mean? I don't know. I don't think it stands for any acronym. It's just the system that does indexing. Okay. All right, so now we focus on how to convert text into a knowledge graph, and that is the RDF triples. So you have here a pipeline of NLP modules, and the text is presented here, and at the end you have the graph representation of the text. So first, there is a module that does document pre-processing. Now this is a very important step, because the documents come in all forms and shapes. Could be double column, could be tables in the documents, could be pictures, could be captions, could be. So the system has to understand what that piece of text is referring to. Right? So the document preprocessing transforms the document into some representation that the machine can process further. Then there is a text segmentation, identifying punctuation and word boundaries and sentence boundaries, paragraphs, etc. Then part of speech, it identifies the part of speech like nouns, verbs, adjectives, and adverbs, and then we go to extracting concepts. These are entities as well as events. Entities are, for example, names of people, companies, and events are things that happen, like our meeting is an event, right? And you extract this is called concept extraction. These modules that have star are customizable modules. They require to be adjusted for just about any other job you do. But whereas the part of speech tagging and document preprocessing could be generic. Words and ambiguation is the module that specifies the senses of the words. Well, if you have the word bank, could be the bank is an institution or the bank of a river, right? And typically that boosts the performance to some systems if you work in some domains. Then is the module that must be there, that is the syntactic parsing. It transforms the sentence into some parse tree. And once you do that, then we have a module that it extracts semantics from the sentence. So the semantic these are semantic relations that are present in a sentence. If I say John went to the shop to buy flowers for his mother, then there are a number of relations there. John is the agent of buying, and buying what has a team of flowers, and where is buying from the shop, etc. Right? So those are the semantics. And extracting semantics from text is really hard, and not too many systems offer this module. Then you have the module of the coreference. This identifies that some names are the same, like John is equal to he, or the professor, or the CEO is maybe the same person. So this module solves those problems. And this coreference can occur even between documents, right? So, or you have an event, like bombing event in one document, and how do you know if it's the same bombing event in another document? So that's the typical hard problem to solve. Then we have the module that is the machine learning. This extracts features that could be used for some applications. And eventually the module that converts the semantics into some RDF representation that will be stored in the graph. So the end result of processing documents will be to have this triple store representation in the graph. And there are many companies offering different kind of knowledge graphs, and it's your choice which one to use. Now, I have here an example that shows you how you go from a sentence to a knowledge graph, okay? And there is this little story here that the train was an Acela Express, number 176. The 176 was scheduled to depart for New York City at 10:30 a.m. and arrive at 1:30 p.m. on March 15. And we parse the sentence, we go through all those modules, but then after we parse the sentence, we identify that 176 is a number, right? So there's a name entity number, and also 176 is a noun, and we have some arguments. These X's and E's are the arguments of the predicates. These words become predicates. So this shows that it's an event here, departing is another event, and there is a relation between event, and New York City is, the machine doesn't know, so it's New York City, and eventually this is concatenated into one concept, New York City, and New York City is a town, and then 10:30 it's a time, and March is a date, and so on. All this is represented directly from the parse tree. So you can automate the creation of this part. What you see here with blue are semantic relations that are extracted from the sentence. So X7, which is this 176, is the theme, the object of scheduling. Schedule what? Schedule for that 176 was scheduled, because this is a passive voice here. So there are some other semantic relations, location, time, topic. Topic is the relation between the verbs and so on. So you can come up with this representation that and that can be automated, and that's a very important step. So this is not like first order logic. It's first order logic cannot be generated automatically. Now, once we have this, then we can generate a graph that. And that step is a very small step. Once you have that previous representation, then you can come up with this graph that X7, it's a number, and it's referring to 176. This is the argument. And between X7 and E1, there is a theme relation, and there is a location relation here between departing and New York City, the time between depart and 10:30 a.m., and etc. You see them here with gold. These are the semantic relations, and the others are entities. And this software can be created to generate this triples. And this is a huge step, because now you have something that is almost like a standard. The semantic triples, RDF triples are called, and you convert text into these triples, and then you can reason about them. Okay, any question? Yes, please.
In your previous slide, you mentioned about the machine learning. Sorry.
In the other slide, yes.
You mentioned about machine learning. No, sorry.
More here.
One more. Yeah. You mentioned about machine learning there. So, what does machine learning do in terms of, in terms of forming the RDF?
Right. It is not only forming these triples, but it's a good question. But you might extract some features that you want to have for question answering, or for sentiment analysis, or for some other applications. So typically that module extracts these features that will be used later on for some applications. So now those features may be linked to the semantic triples if you really want to do that. So the more knowledge you can put in the semantic triples, the better it is. All right. So now let's go to question answering, which was one of the modules in the architecture. So I like taxonomies, because it puts some order into into what is out there, and the thinking, how you approach the problems. One type of question answering is open domain question answering. That means you ask a question, and the question has to be extracted. The answer to that question has to be extracted from a large set of documents. You can have 1 million documents or so, and the documents could be 20 pages or 1 page, really doesn't matter. And you have a question in English or some other natural language, and then you extract the answer to that question. So that's open domain, right? And it could be any domain, financial, could be medical, whatever domain. Now there are other, and the documents obviously comes from web pages and libraries and maps, books, etc. You can even link this open domain question answering with processing images, and that will be even more powerful system. Then there is the frequently asked questions, or CAN question answering. There are situations in which the answer is so important that many companies do not want to venture to have a system pick up the answer, no matter how good the system is, because you can get into some legal troubles if you provide the wrong answer. So you have the question and the answer to that question. So now the problem here becomes, how do I map a new question into one of the frequently asked questions that I have answered for, and how do I increase the number? So we will address that. So having this in mind, I want to say that question answering is not only the information retrieval that we use in all search engines. Like in information retrieval, we get documents back. In information extraction, we have documents and we fill up a template, who did what, to whom, when, where, things like that. And even it's not IR plus IE, it's much more. It requires some processing. Okay, here's an example of easy question. What is the fastest car in the world? And this is a factoid question. And the point I want to make is that just looking at paragraphs where there is a match between the keywords, that is not going to be good enough, because you have the fastest and the word and the cars here in this paragraph, but this is not the answer we are looking for. The answer is in this paragraph, right? And the answer is this car. Well, that was an easy question, a factoid kind of question. And then there are more difficult questions, like will the Fed change interest rate in their next meeting? I had this slide even 10, 15 years ago. It's still valid, right? Because the Fed still does its job. So to answer this speculative kind of question, you have to acquire information about the Fed, interest rates, and then stock market, employment, and inflation. You have to extract all this piece of information. You got to have a model, and then through that model, you will be able to figure out if this is going to go up or down or stay the same, right? So it's possible to attempt to answer those hard questions, but not immediately. You have to extract more information. A taxonomy of the question answers is over here. You have simple questions like what is the largest city in Germany? And the answer is Berlin, the largest city in Germany. So there is a snippet of text giving you the answer. More complex questions will be questions where you have to do some reasoning to pick up the answer. How did Socrates die? Well, Socrates poisoned himself. So you have to figure out poison himself is related to dying. It's one form of dying. Or you can have questions like you have to put together the answers and come up with a list. What are the arguments for and against prayer in school? And one part of the answer comes from one document, another from another document, and the system had to be smart enough to come up with a list of arguments for and against. And then there are interactive questions like clarifying questions, like chatbots or dialogue systems, right? And these are considered to be more difficult. And then speculative questions that I mentioned before. So, so the state of the art is that systems today, even Watson, can answer this factoid question like in Jeopardy. So the factoid question that they answer. But certainly when it comes to even some more complex reasoning, the systems break. They are not able to answer these complex questions. Never mind the complex questions that are category 5. So generic question answering architecture looks like this. You have the documents, and could be very few or many documents, and the question goes to question answering system, and you have to pick up the answer. Now, the answer, some people want to have the exact answer. Who is the mayor of Dallas, for example? There is a name, right? You have to be careful. You have to give today's mayor of Dallas, not, I don't know, 10 years ago, mayor of Dallas. So there is some reasoning that has to be carried in order to provide the correct answer. If you look at more details, what's under this box, you have a module that processes the question. So the question has to be understood. If you do not understand what the question is about, there's no chance for getting the answer. So we have to form a query, and we have to know the intent of the question, the focus of the question, the type of answer we are looking for. And the traditional question answering sees this query and retrieves documents through Solr or some other information retrieval system and gets some relevant documents out of the million documents that you have up here. And once you have very few documents, then you do the hard work to extract the answer from those documents. And this query goes there, and then you eventually have the answer. And there are some resources that could be used, like even Wikipedia or some dictionaries or CIA Fat Book and many other repositories that provide some partial answers. Now, if we look at more details about the architecture, this boxes here with orange color are part of the processing question. So first, we have to figure out the spelling and how to split the question. Maybe the question can be broken down into two simpler questions. So you do that there. Then you construct internal representation of the question, and you have to pick up the answer type. What is the question all about? And we have to select some keywords. If the question is very long, then some keywords will be eliminated. Only the important keywords will be kept in a query. And eventually, sometimes we have to form the query expansion, like what's the capital of Texas? Here you just have Texas and capital, so we have to look for some other words that are related to capital, because capital could be ambiguous. It's just a town or maybe some capital, like a monetary or something that Texas has value. So anyway, at the end of this, we form the query, and that goes to the information retrieval and extracts the passages where potentially the answers come from, and then we identify the answer in these three modules, like a candidate answer. We rank, and sometimes the system gives you a list of answers, and they all have some figure of merits, and then you have to pick up the one that you think is the most likely answer, and then there is answer formulations. So this is a more detailed architecture of a question answering system that typically has been implemented. Just for you to have an idea where the errors are occurring, most of the errors are occurring in this detecting the answer type, and also when we expand the query from simple query to larger queries to capture answers, and even the identification of candidate answers. So there are some numbers here that indicate the percentage of the errors produced by each module. One innovation of this architecture that has been well received in literature is to provide some feedbacks for those sequential modules, sequential architecture. And in case you do not have enough passages that can contribute to the answer, then you go back and you retrieve more passages. And if you are not satisfied with that, you go back and you change the query formulation. So these feedbacks provided an improvement in generating answers, because you don't have to give up. You work the system and the documents until you get the answer that you want. All right. Some complex questions that could not be answered with that system are listed here. And these are some questions I looked at recently for an investment institution. And what the analysts, this is an analyst working for that institution, top recommendations now, right? So here's the name, John Blow's top recommendations now. So we have to figure out what the recommendation is. And for that, we need an ontology, because just the word itself, recommendation, doesn't mean much to the system. But if we have an ontology, then this is translated into stock recommendation or some other securities. What are the key value of growth drivers for a certain company? Right? It's another complex question that requires an ontology. What are the terms, risk, or concerns for a certain company, right? These are all questions that analysts are asking, and like I said, to answer these complex questions, typical question answering system will not be sufficient. So what's the problem? How do we solve this problem? Well, we build an ontology that's specific for that domain, and then we take each type of the question and we try to have patterns for figure out how to create an answer for each pattern of the question. So it's not as simple as matching the question graph with the knowledge graph. That will fail. Now, so the point is that since we cannot provide answers only by matching a question graph with a knowledge graph of the document, then we have to use a hybrid approach, and that means to use Solr that will provide indexing. So through Solr, we index the document, and this is a more robust. Yes, please.
Sorry, what does RDF stand for?
RDF is a standard for
Rich document format?
Format, yes, thank you. Yeah, we use that all the time. So it's a standard for semantic triples. Yeah, and so this alone will not be sufficient, neither will Solr be sufficient, but the hybrid approach is superior, because sometimes you get the exact answer to some difficult questions by matching the graphs, but sometimes just the information, the indexing will be sufficient. All right, so I was mentioning ontologies, and like I said, how many of you are using ontologies in your work? You are using, I think, more and more. And there are jobs like ontologists now that are, I've seen companies are hiring, and they're looking for ontologists, and there are not too many of those on the market, so they are very well paid. The role of the ontology is to create some knowledge that links different concepts, such that if you look for a word like that doesn't have much meaning, but then through the ontology is connected to other words, then that will enhance the query, and you can get the answer here. All right. Here's an example of a question. What are the key stats for Microsoft in the last quarter? So we have a matrix here, key stats, we have a company, and we have the time, and the answer is coming from this sentence. Now, how do we link that question to this sentence? So Microsoft, that's a ticker. Then we have the word revenue, reach 1 million in fourth quarter 2017. So the key stats is linked to revenue through the ontology. And then we know that revenue is 1 million. That's easy to find out. Microsoft is a company, and this is a time for the last quarter, and then here's the answer. So without ontology, it will be difficult to provide such an answer. If you're interested, this is an ontology that shows, for example, how the word recommend links to stock, to shares, to assets. So the indentations mean ISA relations, right? So asset is an ownable, economic asset is an asset, financial asset is an asset. So these indentations represent ISA relations. And the recommended is here under the stock. Okay, so you can answer a question like that. What is our recommendation on VMware? Well, we have to understand what our is. It's the analyst's view, and then the recommendation is picked up from there. It's a stack value, and VMware is a company. So you transform this question into some semantic triples, and then you can get the answer, hopefully. All right. The English question, which is shown here, can be translated into a Sparkle question that it's sent to the knowledge graph, and that transformation from English to Sparkle is automated, can be automated with a little bit of effort, because people don't want to use Sparkle to query the graph. So instead, you have this module that converts English to Sparkle, and then this is sent to the knowledge graph, and then you can get the answer from there. So it's possible to do that, but it's not so simple. It requires a little bit of effort, but it's possible. Now, I'm coming to frequently asked questions. These are the other type of questions. And I'm using a use case that we had for Fannie Mae. If you look at the web page, there are 22 frequently asked questions, and those questions have answers. And this is an example of a question and the answer. Okay, so, but what can you do with just 22 frequently asked questions? Typically, a user may ask a question that is in total different format. So now the task is to make sure that that question maybe links to one of the existing questions, the same as one of the existing questions, and then if that is the case, then you have the answer for that question. So here the problem is how to generate questions that are semantically similar, they are paraphrased. So for that, we use a neural network module, a BERT system, and data augmentation. So we have a question, and then the data augmentation first takes some words at a time, and then for each word, it generates lexicosyntactic pattern. So for example, if I have a question like, can I see something? Then through this augmentation you have, is it possible to see something? Or is it allowed to do something? So that's what we mean by this augmentation. So there are patterns that are replacing words, and we generate more words into data such that the questions are semantically similar. And then through the neural network, we can generate even more words that are related to those words because of the semantic similarity of the vectors. And then eventually we end up with a model. So we use this architecture, and we generated for those 22 Fannie Mae questions, 58,000 automatically generated frequently asked paraphrase questions. And that was large enough to satisfy people asking all kinds of things about the Fannie Mae web pages. So that's a large number. Okay, and the accuracy of the generation was about 91% with the BERT model. Okay, so in order to, yes, question, please.
Does that mean that 9% of the questions didn't have an answer, or they were?
No, that means they are wrong matches. They did not match correctly.
Okay.
That's what 90% indicates. 90% of the times the questions match.
But does that mean that they were inaccurate with mapping toward an existing fact, or that they were completely different questions?
If they are completely different, they are not considered here. So we only consider questions that had a match, but they missed. Yeah, because we want to know how good the system was.
And is that through, thank you. Is that through real data testing, meaning real populations?
Real population, yes. Those I'll show it. Well, here are some examples of questions. Let's see. Well. Okay, so this is a original frequently asked question. For employment offers and contracts, if the lender is unable to obtain a pay stub to meet the selling guide requirements, do we have options? Now, what we did to help the system, we manually generated about 15, 20 questions that are different, but they are semantically similar. So you generate that in 1 hour or two, right? And then just to help the system to generate even more questions automatically. And this is a question that was generated manually. What are the options if the lender is unable to? So this is exactly the same question, but different words. And then the system pick up paraphrase questions either from there or from here, and you have here at least 3 examples of questions that are semantically similar to these questions that are part of that 58,000 questions. So these questions are pretty real, right? If you read, there's no nothing strange about this question. These are how people speak. So that's pretty good. Yes.
Excuse me. I just want to clarify RDF.
Yes.
It also stands for Resource Description Framework.
That's what I mean. Yes.
That's, I think, what you.
Yes. That's what I mean. Yes.
Not the documents, but to the.
That's right. That's right. It's from the semantic web. Yes.
Can you give us a little more details about how those paraphrases are automatically generated? Is that a natural language generation model?
Yes. So let's go back. Okay. So there are two steps. One step is to look at the question and change the words. Come up with some. For one word, you replace the word with a phrase, like a verb phrase. Like I gave the example before. Can I see through that window? Is it possible to see through that window, right? Am I allowed to see through that window? Things like that, right? So,
is a human doing that substitution?
No,
or is that the machine doing?
Those are done automatically by the machine.
So and that's a lookup into a thesaurus or a dictionary?
Exactly. So some work has been done to come up with the lexicon for this data augmentation. But you do that once for all and you have it. So that's one step. And then you go to the next step through the BERT system that takes a question from here and generates even more questions here by the virtue of the language model, right? So
you use BERT for that?
BERT for that, yes.
Okay.
Yes. Right.
Thank you.
Yes. Right, so this worked very well, and like I said, there are many companies that are valuing these frequently asked questions because they want to make sure that the answers they produce are absolutely correct, and they are not liable to any misinterpretation and so on. Now, here's the input text that the user asked, like, can the realtor commission go towards the borrower down payment? So that's a question somebody is asking, and then that maps to this question, which is frequently asked question, for which there is an answer. So, like I said, the problem is how to generate this. The questions that are generated. In other words, the user doesn't have to use exactly those words. It can, the user may change some of these words, but then the new question, let's say the user can use some other words here. Then through the neural network, then this is considered to be similar to that question for which there is an answer. So those 58,000 questions are not the only questions that somebody can ask the system. Right? There are other questions that can be similar to those 58,000 questions. So very, very large number of questions. Yes, please.
Excuse me, and what do you use as a measure of similarity?
So we try to be here very strict about similarity. So in the literature there is this semantic evaluations, and they use 5 degrees of similarity: 0, no similar; 1, a little bit more, but still not similar. If you are level 3, they are close, level 4 is closer, and level 5 is very good similarity. So there are these five levels that I use in the literature. And you can put the threshold. You accept only level 5, level 4, and those are considered very good similarity questions. So that's what I mean by similarities, right?
So my question is, how do you determine if it's 2 or 3? So what's the cost function you use, or what's the...
There is the measure of belief. There's the probability. Right. So the similarities basically derive with a neural network, and then you have the outer layer, the that gives you the probability of the output, and that's how that is mapped into those levels 2, 3, 4. Yes. All right. Now, the last topic I want to touch upon is it possible to build a question answering system with neural networks, right? And I know many of you are interested in that. Well, here's the answer. First of all, I just want to say that for neural network, we have to have some collection of documents to train the system. And one collection is the track system that NIST, the government agency NIST, has prepared over the years, and there are some competitions. In fact, the precursors of Watson system was part of that competition, so is Limbaugh. So there are about maybe 5,000 questions, and there is 1 million documents, and there are answers for those questions. So if you want to train your question answering system, you can use the track collection. Probably there is some paperwork to be done, but they are generally available. So that's one good resource for training. The other one is the SQUED, the collection of paragraphs from Stanford. There are about 100,000 paragraphs and questions, and the answers could be in those paragraphs or could not be in those paragraphs, right? But the difference between the two is that here you have 1 million documents, and some of them are long documents, and here you have only paragraphs, right? So the work in question answering is only about the SQUED collection, right? They never attempted to come up with a solution for the track collection. Why? Because you have to retrieve documents. It's not possible to process through neural network 1 million documents, right? So here's the architecture. Here's what's going on. We have a question, and then first we still pre-process that question to find out the user, the question focus, what's the question about, what type of answer we have, etc. Those modules that I mentioned at the beginning are still useful here. And then we have to, if we have a collection of documents, like in this case, we have to have an information retrieval system and to pick up the paragraphs that are potentially keeping the answer. And then the question and the paragraphs will go through the neural network model. Because here, you don't have documents. You are dealing with some paragraphs that have been already produced by the IR system. And then we use BERT, and we use also Excel, which is much better because it can input larger paragraphs. I mean, BERT is only taking 512 tokens, but XLNet allows you to input much larger paragraphs, thousands of tokens, right? So then you get the answer. And the answer you get here is very good. So this part of the architecture works very well. The part where it doesn't work is this. The neural network cannot replace the information retrieval. In other words, you cannot have here 1 million documents and send them through the neural network to expect to get some answers. You have to couple that with the information retrieval in order to get answers. So here's the architecture that's BERT. So here's the question, and there is this tokens that separate the questions from the paragraph, and this is the paragraph that may or may not contain the answer, and then the output will be the word that starts the answer, if there is one, and this is the word that ends the answer. Right, so here, I think I have an example, some examples here. What is the largest volcano in Europe? And the answer is Etna. So in the BERT architecture will be only one word that is the answer. In this case, the beginning of the answer will be pointing to this quotation, and then this will be the end of the answer, right? So because that's the answer. Okay. Okay. Any questions before my final slide? Some takeaways. All right. So I think that NLP tools allowed us to build robust AI systems. We have parsers. We have semantic parsers. We have word disambiguation. Now, these tools are not necessarily part of your open source repository. For example, open source does not have any semantic parser tool. Syntactic parser, yes, but not semantic parser, nor does have coreference and some other. So there are some sophisticated tools that have to be built or in some laboratories and so on. But these tools exist, and they're becoming more and more popular. And with those tools, we can convert text into some semantic triples, and then we can do case-based reasoning or some other common sense reasoning that was not possible to do on a large scale. So, not only toy systems. Then another idea is that it's possible to transform text to knowledge graphs and perform reasoning. And that representation, the representation I show you, goes directly from a parse tree to semantic triples without creating the first-order logic axioms, which are difficult to create. So we make some simplifying assumptions. We don't need the quantifiers and some other sophistication that first-order logic has. So we renounce that, but then we end up with building more robust representation. Dialogue systems using natural language and question answering is a powerful architecture that enables new applications, which is a big step towards really intelligent assistants. So now, of course, we didn't talk about the intelligent assistant being able to ask questions, right? Because the clarifying questions, nor does it have any personalities. So there is a long way, but I think those things could be added on top of that architecture that contains the NLP and modules and the question answering. And last, the fact that neural network technology changes NLP, and really, I've seen if you go to an NLP conference, about 60% of the papers are related to neural networks. It's amazing, and everybody's in the universities and research is doing deep learning NLP. But neural networks alone are not enough. And I had an example where it had to be coupled with information retrieval to really solve a problem like question answering.
Could you comment a little bit more on the state where the answer retrieval is not from a non-structured data, but from a structured data? So, for example, in a customer service use case where some customers are maybe asking questions about, their balance, if it is a banking, app, for example, how is that different, or how has there been sort of a research or advancements in those areas where the Q&A system is retrieving the answers both from the non-structured as well as from the structured data? Right. So there is the trend mixed the databases with knowledge bases. Right? So databases, as we know, cannot sustain reasoning, but knowledge bases do. And if you combine the two, you have to change the representation. You have to convert into some semantic triples. And the relational databases will merge with the knowledge bases. So I think that's going on. If you want to do other things other than just retrieval from the database, you may want to reason about knowledge, you may want to restructure the knowledge and so on. And databases alone cannot do that. So I think that's where the work is, to combine the two. As far as question answering is concerned, it doesn't matter what triples are you retrieving, data or knowledge, doesn't matter. So you convert the structured data into that. Yeah, in fact, you can even convert images into semantic triples. And then you have a unified representation, and then you can extract from text and images. And we know that one complements the other. So then you can have more interesting question answering system. Please.
So when you identify a match to a question in the knowledge store that has RDF data, are you taking the RDF answer and converting it from RDF into like human sounding text, or do you actually use it to reference like original text from like an original?
Could be either. Typically, you go back and you identify where that came from, because to convert from graph to, we have not done that. But that points to the knowledge graph. In other words, has pointers. We always point back to the text. It was missing in the URLs were missing in my slide over there. But each object there has a pointer to the text. So you go back and you retrieve from text. Yes.
I have a two-part question. The architecture you just described, it's something you think works for a robust system. To what extent is this the industry standard, and is this where everybody is compared to what you think it should be?
You are talking about this architecture.
Yeah, and basically what you just walked through in the presentation.
This architecture, right?
Yes.
Okay. So there is an architect. I made this architecture last week because I was kind of preparing for the talk, and I was thinking. There is an architecture that is in textbooks and research papers, Bellegarda's architecture, and it does not have the question answering, does not have the knowledge graph, nor does it have ontologies. What they have is they break this dialogue system into some modules. So it's more concerned about this orange.
So this is far from any kind of accepted best practice. This is something that you think
yes,
would work.
Exactly.
The second question I have is, does this have anything to say about the question of generalized AI as opposed to specific AI, domain-specific AI?
Right. Well, there is no such a thing as general AI, because we know that you build an AI system for medical domain or for something, and is not applicable to some other domain. In other words, knowledge is not linear. And we cannot really build a system that it's working in any domain. You have to have common sense knowledge. You have to have axioms for that domain. And but I think with the architecture that I show that goes from text to the RDF representation, that's a huge step. And you can build the knowledge bases that can contain many common sense,
Okay, thank you.
Yeah.
So you mentioned BERT as kind of an example as the neural network that works alongside this. Are there others that you've tried out? Like certainly BERT's made a lot of news, but what would make someone choose BERT over something else to move alongside here?
For example, we have used CNN, convolutional neural networks, for classifications. They work very well for classifications, but we try to use them for question answering or for some semantic relation extraction, and they do not perform well. BERT was found to work very well for some of those modules, because if we look at the pipeline, this pipeline, there is neural network activity in all these steps. It's not only here. Even part of speech tagging can be done with neural network, or concept extraction. Certainly, semantic relation extraction can be done with neural network. But we find out that we did it with BERT, and now with the XLNet. Different architectures. Very interesting fact that we just found out last week. BERT has 12 layers. The base system, and the large system has 24 layers. Well, we want to know, because it's a little bit slow, so we want to know how many layers will do still a good job. Turns out that 2 layers will be sufficient, and you're only missing about 1 or 2% of accuracy. So if you want to have a speedy neural network architecture, get rid of 10 layers of BERT and still get good results.
That's actually great to hear, because a lot of people kind of complain about the heft of it. So
yeah,
thank you.
Yeah. Because we are trying to look at Well, what's going on in each layer? And we're thinking that the first layer does some part-of-speech tagging and then some syntax, and only the upper layers will be involved in semantics. Well, it's not like that. We could not identify that lower layers are good for syntax and upper layers for semantics. No, the machine starts to pick up weights very early and then just refines those weights. So that was an experiment we did last week. Yes?
This is a deterministic model that you have right here.
This? Sorry.
Yeah.
This is a deterministic model.
Yes. And so what my question is how are you weighting? Well, the first question is this sequential, or is it all happening at the same time with, self-referential feedback? And then, I'm sorry, go ahead and answer that one.
Unfortunately, the language is sequential, and you have to go through this module. Now, you may skip word sense disambiguation. Let's say that you are not interested in, you just go by default and pick up the most popular sense in WordNet, for example, and you live with that. So you don't do any work for word sense disambiguation, and that may work, But if you really want to squeeze every drop of performance, then you want to have a good word sense disambiguation.
But I'm correct in assuming that I start at the top and I work my way down?
Yes, exactly. And you want the top modules to be as performing as possible, because if you make mistakes there, it's difficult to recover. So if you make some mistakes here, something is a verb or instead of a noun, then the syntactic parsing fails and so on. That's the problem that we're having in natural language. It's a sequential activity. Now, humans do it differently, and maybe, who knows, 10, 15 years from now, maybe there will be a neural network from text to the end. Who knows? Maybe it's possible. But right now, we have to go through these modules one at a time.
Okay, so then in the levels in your neural network, is there some explainability in which one of these deterministic parameters are being held?
There is a lot of research trying to understand what's going on in neural networks. It's not easy, because you're dealing with a lot of parameters, maybe millions and millions of parameters, weights that have been decided, and what they mean, and it's very difficult. But there is a lot of research in that area by universities.
Thank you.
Yes.
Is there any sort of reference architecture or something someone can pull down and just have even just a simple way to go through this pipeline, plug in some of the open source tools? Like here.
Yes. In fact, let me tell you what's available in open source if you're interested. So document preprocessing is not. And document preprocessing includes, in our opinion, processing tables. And a lot of information is in tables. And tables can be of different formats, multi-column, multi-rows, and etc. Very complicated. And you have pictures, you have captions, and so on. So to make sense out of document, and I've seen documents that are 1 page or 600-page documents, regulations, and so on. So it's a very important step there, but it's not available. Text segmentation, yes, is available. Part of speech is available to some performance, not commercial grade. Concept extraction, yes. Word sense ambiguation, I think there is, and certainly semantic parts, but that's where it stops. And there is no semantics as part of the open source offerings. Right? So it stops right there. So it's up to you what you want to do later. Now, for some applications, maybe that's enough. And you have entities, you have events and concepts extracted, syntactic parsing. So if you want to do some simple application, it's okay. But certainly not question answering or some other heavy-duty applications. So.
All right. Thanks so much.
Thank you.